Hi everyone, so I'm going to go ahead and go through number 25 now from chapter 7, problem and exercises. So on this one we're going to start the same way as I did last time. So remember, we always start with this giant thing. So our potential gravitational energy plus our potential spring energy plus any kinetic energy we have, plus any other work. Okay, and that's going to equal our final gravitational potential energy plus our final spring energy plus our final kinetic energy plus any heat that we have. Okay, so this problem says, so we'll start with part A. It says, how high a hill can a car coast up if the work done by friction is negligible and the initial speed is 110 kilometers per hour. Okay, so on this one, we are actually starting with kinetic energy, right? So we have 1/2 mvi squared. And everything else seems to be negligible, so the only thing that we're ending up with is gravitational potential energy. So mg YF. Okay. So now what did they ask us for? How high up we're going to get. So what our Y position is going to be at the end. So we can solve this for that by dividing everything by mg. And so we end up getting YF equals VI squared over 2G. And then our VI is 110 kilometers for every 1 hour. And of course, we need to convert that to meters per second. So we know that there are 1,000 meters for every 1 kilometer. And we know that there are 3,600 seconds in every hour. So we can calculate that out. 110 times 1,000 divided by 3,600. And that is 30.6 meters per second, because hours cancels, kilometers cancels, and I'm left with meters per second, just like I wanted. Okay. So now I can plug it in. YF equals 30.6 meters per second squared divided by 2 times 9.8 meters per second squared. So now I have 30.6 divided by 2 divided by 9.8. Is 1.56. Doesn't seem right. Oh, I forgot to square everything. Or just this. 30.6 squared divided by 2 divided by 9.8 is, that looks much better, 47.8, and then I've got meters. When I square this, this becomes meters squared per second squared. So one of our meters is going to cancel, both of our seconds is going to cancel, so we're left with meters. It's a nice little check to make sure that we did everything properly. So that tells us where we end up. And now for part B, we find out the sad truth. In actuality, the car, now they're telling us the mass of the car, it only gets 22 meters above the starting point, so it doesn't go all the way. How much are we losing to friction given that? So we know that our heat, so our work done by friction, well, let me start from our main thing here. So we've got the same situation, right? We have 1/2 mvi squared equals mgyf, but now we have heat. So plus work done by friction coming out of the situation. So now if we solve this for friction, then we can plug in all this stuff and figure out what, how much energy this is. So the work done by friction is going to be 1/2 mvi squared minus mgyf. So the work done by friction is going to be 1/2 times the mass, which was 750, times the initial velocity, which was 30.6 squared, minus the mass, which is 750, times 9.8, times the actual height, which is 22. So that gives us that the work done by friction is 1.89 times 10 to the 5th, and then that's our energy, that's unit of energy, so that's going to be in joules. So that is our answer for part B. And for part C, it gets even more interesting. So now it wants to know, what is the average force of friction if the hill has a slope of 2.5 degrees above the horizontal? So now we know that this is 2.5 degrees. I don't know why degrees is right there. And that's our theta. We know that we've gone up 22 meters, and that's our height. And we know that the work done by friction is going to be equal to our force times our distance, right? Our distance is going to be this. So that's what we have to figure out. And then we're going to plug this back in because we already know this, right? We can figure this out, and we're trying to find this. We're trying to find the average force. So we're going to end up with F equals the work done by friction divided by D. So D, our friend D here, is we can use our trig functions, right? So we've got opposite over hypotenuse. So D, well, let's just write, so we've got sine theta is going to equal our opposite over our hypotenuse, our H, divided by our D. So if we want to find D, we're going to get that D, I'm just going to erase this random D that I have written here. D is going to be equal to, so we get D sine theta, so then we get H divided by sine theta. So now we can plug that in over here. So F is going to be equal to the work done by friction. And then we got to flip this guy upside down because it's underneath. So times sine theta divided by H. And then our work done by friction is here, 1.89 to the 5th times 2.5 sine divided by 22. And that gives us a force of 375 newtons. So that is the last part. That tells us what the average force of friction is going up that hill. So I hope that helps. There was a lot going on in this one, but see how we started here and then we just used our basic tools to get all the way down to the bottom. So it's just new situations of applying your old tools. Okay, I hope this helps.